Most of the time, when a drop of water falls onto a larger surface of water, it's quickly absorbed and then coalesces into one large body of water. But sometimes the conditions are just right so that you get something called cascading non-coalescence, and it looks like this. A drop of water falls onto the surface of water, but it isn't absorbed completely. In fact, it bounces off of it. But then it quickly snaps into the bulk water, and it happens so fast that the water springs back up and forms another tiny droplet. And this process happens over and over again, decreasing the droplet size in the process, until finally the drop disappears completely. The slow-mo guys recently posted a video showing amazing footage of this effect. But why does it happen? Normally, water really wants to stick to other water. This is because the surface tension of the water wants to minimize the total surface. So one big drop has less surface area than two smaller drops. So if two drops touch, they snap into one big drop. That's why normally when you mix two streams of water together, they usually make one big stream. But this isn't always what happens. Sometimes you'll see what looks like tiny little bubbles on the surface of the water. But on closer inspection, you'll see that these aren't bubbles at all. But they're actually tiny drops of water rolling along the water's surface. This phenomenon is called non-coalescence. Non-coalescence is fascinating, and it shows up on more than just single water drops. But sometimes when you have two streams of water flowing onto each other, they'll just bounce off of each other, as if they're repelled. But why? What causes water to repel itself sometimes like this? Well, let's investigate. What could cause this non-coalescence? And let's see if we can control when it happens. And we'll see that if we can figure out why it's happening, then it might be possible to make non-coalescence that's permanent. Not just a fleeting moment of non-mixing water, but a permanent water drop that won't mix with other water. And before we continue, I just need to read this top secret letter I intercepted from Franklin D. Roosevelt to Dr. Oppenheimer, the head of the research team that developed the atomic bomb. This letter was mailed to me by Historic Mail. Historic Mail is a thoughtful gift for anyone who appreciates history and the lost art of letter writing. It also makes a great gift for people who already have everything. It was started by a group of history enthusiasts who relished the idea of getting letters from historical figures weekly, almost as if directly from Benjamin Franklin's or Thomas Edison's desk straight to yours. Every week, a stamped envelope is delivered to your doorstep containing the reproduction of a letter penned by a famous historical figure, supported by a document providing historical context and a typed version of the letter. I love seeing copies of the actual letter because you can see the personalities in the writer coming through. For example, look at this letter from Roosevelt to his son, with even a story he wrote to go along with the pictures he drew. You get to learn about the fascinating inner lives of the greatest historical figures from the primary source itself, and be reminded of the forgotten episodes from the past. The American History Gift Pack covers letters from 1776 with the founding of the Republic all the way to 1976 with the Cold War at its height. It features letters from presidents such as George Washington, Abraham Lincoln, and Franklin D. Roosevelt, as well as other great historical figures who greatly influenced American life, such as Walt Disney, Tesla, and Twain. It really is the best gift to a history lover. You can also send a beautiful gift certificate with your name and the receiver's name on it to make it even more personal. Historic Mail offers 10 weekly letters for only $59.99. There are also letter packs for 25 letters and a yearly pack of 52 letters for more in-depth exploration through various periods of history. Historic Mail is the perfect gift for history lovers. So this holiday season, remember to surprise your loved ones with this timeless gift. Enjoy 10% off on all their products with their Christmas sale. So go to historicmail.com/action to get your gifts now and help support the channel. Now let's get back to our experiment. In order for water to mix with other water, the surfaces have to be able to touch. And in order for the surfaces to touch, the air that's in between them has to get out of the way first. In pure water, for a fleeting moment, the air can get trapped in between the water surfaces, and they don't touch. But eventually the air gets squished out of the way and the two water surfaces touch. Once they touch, the surface tension quickly snaps them together. When the water has impurities in it, then it changes the surface tension of the water, and it makes it easier for the little air gap to stay in between the two water surfaces. If you add a little soap to the water, then it decreases the surface tension of the water, allowing the non-coalescence to happen much longer than pure water. You can see when I drop some water with a little soap in it at just the right height, I can consistently make non-coalescence happen on the surface here. So even though these two liquids are exactly the same, for a brief moment they don't mix due to the small gap of air in between them. This can even happen with flowing water, like I mentioned. So I have a container here that I'm just going to pour some water in, and some tubes at the bottom, and the water can flow out of it, and I can mix the streams together at the bottom by aiming them at each other. Now I'm going to start off with just pure water. It's not soapy water, it's just coming straight out of my tap. You'll notice that right at the beginning, when the pressure is the highest and the streams are shooting out water the fastest, then the water streams mix like normal. But something interesting happens when the velocity of the streams decrease. They start to repel each other and not mix. The streams are repelling because they're entraining a small layer of air around them that doesn't allow the two streams to actually touch. So the air is continually being dragged in between the two streams. And if I add a little soap to the mix, then you can get this effect to occur even stronger. I was even able to get 3 streams to repel each other simultaneously. Now this is amazing because these are all the same liquids. Normally when something's the same liquid, it attracts itself. There's a saying in chemistry that says like attracts like. So we see that if we can continually keep air between the two liquid surfaces, then we can get persistent non-coalescence. But is it possible with a drop of water as well? Well, one way to continually keep the air pocket around the drop of water is by continually vibrating the water. So if I make standing waves in the water, then you can make non-coalescence happen really easily and last for a lot longer. Destin from Smarter Every Day has a cool video that shows the same effect that he made a while ago. Okay, first without shaking, you can see that non-coalescence happens a little bit. So it does happen, but it goes away pretty quickly. But now I'm going to turn it on to 18 hertz. Look at that. It's just staying. When I hit the exact right frequency of this vibrating plate, I can get the drop to last for a long time. It's just permanently staying there. So this is permanent non-coalescence because I'm continually vibrating the water. My record is actually around 15 minutes for one single drop that just stays floating on the surface. You can see that once they form, they just bounce on the surface of the water continually, never mixing. Look how cool this is. What's cool with this is if you change the frequency and amplitude, you can even make it so that you get continual droplets on the surface without adding drops, because the waves are peaking and making little droplets that break off and run along the surface of the vibrating water. So I propose that it's actually the air in between the droplets and streams of water that keep the two liquids from mixing. But is that really the case? Well, if it was, it would depend on the properties of the air around the water. I found a research paper that showed that non-coalescence was pressure dependent. So let's try to see if we can get it set up inside my vacuum chamber and see if the effect goes away at lower pressures. So I have some water with a little bit of soap in it so the effect happens a little bit easier. And I'm going to put some of that water in the syringe and it'll just drip out into a beaker below it. At atmospheric pressure, with almost every drop, they just roll along the surface of the water. Okay, this is full pressure. But as I drop the pressure, the effect just goes away. Okay, we're at 0.6. 0.4. Okay, so at 0.4 we're getting no beads. But if I let the air back in now, then the beads form again. So it really is pressure dependent. The higher the atmospheric pressure, the more you'll see this effect. It's really neat that we could confirm it so easily how this effect is working. And thanks for watching another episode of the Action Lab. I hope you liked it and learned something. If you did, don't forget to subscribe to my channel if you haven't yet, and we'll see you next time.